Right now, at this exact moment, something may be traveling through you. Not light, not sound, not even the familiar tug of gravity doing what gravity always does. Something without a name in any published textbook. Something that moves through the iron in your blood and the calcium in your bones and the water filling your cells and registers absolutely nothing. No heat, no pressure, no disruption of any kind. The only reason anyone even suspects it might exist is because a subatomic particle no larger than a mathematical abstraction moved through a carefully constructed ring in the American Midwest and wobbled a fraction of a degree too far. That single wobble, quiet as anything that has ever happened in a physics laboratory, may be the first faint impression of a force connecting everything we can observe to a hidden layer of the cosmos that constitutes the overwhelming majority of what actually exists. Settle in, subscribe if you're new here, and stay close because the further you follow this thread, the stranger the world it leads to. There is a clean version of this story, a version in which the machinery operated perfectly, in which every calculation came back matching every measurement, in which the most successful scientific framework ever assembled continued its unbroken streak of being exactly right. That version is tidier. It is also not the version we are going to follow because something arrived in the data that was not supposed to be there. Not a catastrophic failure. Not a dramatic collapse of theory in a spectacular explosion of contradictory evidence. Something considerably quieter. A number. A deviation buried in the 9th decimal place. A quantity so deeply embedded in the scaffolding of precision physics that you would need years of graduate training before you could even begin to articulate why it ought to concern anyone at all. And yet it concerned them enormously. Because in this particular field, a deviation of that scale is not a rounding imprecision. It is a tear. Before we can feel the weight of what happened, we need to understand what was there before the anomalies arrived. The standard model of particle physics is not merely a useful tool or a practical approximation. It is, in the most direct and unexaggerated sense, the most accurately predictive theoretical structure human beings have ever produced. It describes the elementary constituents of matter and the forces through which those constituents interact, with the sole exclusion of gravity. And it does this with a fidelity that has no precedent anywhere in the sciences. Its predictions match experimental measurements to 10 and 11 decimal places, not approximately, precisely. This is comparable to predicting the driving distance between two cities on opposite sides of a continent and being correct to within the diameter of a coin. That is what generations of physicists built. That is the standard against which a wobbling muon was being compared when the data started behaving unexpectedly. The history of this field explains why a small numerical mismatch carries so much weight. Particle physicists are not a credulous group. When a result deviates from prediction, the immediate response is suspicion directed inward. Suspicion of the calculation. Suspicion of the instrumentation. Suspicion of hidden sources of error that no one has yet thought to account for. Independent teams are assembled and handed the raw data with instructions to find whatever the first team missed. This process consumes years. The entire professional culture of the discipline was shaped in an era when falsely claiming a discovery was regarded as one of the most serious failures a researcher could commit. The bar for announcing genuine new physics is set at what the field calls 5 sigma, meaning the odds that the observed deviation is a random fluctuation are smaller than 1 in 3.5 million. That threshold was not chosen arbitrarily. It was earned through repeated painful experience with 3 sigma signals that collapsed into nothing when better data arrived. So when researchers at Fermilab in Illinois and at CERN in Geneva began seeing measurements that did not cleanly agree with the standard model's forecasts, their first instinct was not celebration. It was suspicion. They went back through the analysis. They audited the equipment. They brought in fresh perspectives. They stress-tested every assumption. What makes this story worth the attention it demands is that they kept looking and the deviations kept surviving. Quieter, more modest than a smoking gun, but persistent. Not resolving into noise, remaining, like something that would not leave. Here is the question that this entire investigation circles. Hold it from the start. Is it possible for a fundamental force of nature, a genuine interaction between particles, to pass through ordinary matter so completely, so selectively, that physical detection is not merely difficult, but structurally prohibited? Not a technology problem, not a funding problem, a physics problem. Impossible because of what matter is and how the rules govern its behavior. And if such a force exists, how do you ever know whether you actually found it or whether you spent years staring into data that your own hope shaped into a pattern that was never really there? This is not a story about a confirmed discovery. It is important to say that plainly before we go any further, because the actual situation is more interesting than a clean announcement would be. What happened is this. A signal appeared, grew to a level that attracted serious scientific attention, generated enormous theoretical momentum, and then began to flicker. The certainty that everyone wanted to attach to it proved resistant to attachment. The anomalies we are going to follow, a muon precessing slightly too fast in a superconducting ring in Illinois, and a quark decaying with a subtle bias toward one particle type over another at the world's largest collider, came from two of the most meticulously engineered and analysed experiments in the history of physics. They were taken seriously by serious people. For a span of years, they generated genuine, carefully hedged excitement that something in the standard model had finally revealed a seam, a crack, a gap through which something from outside was pressing. The deeper possibility, the one lurking underneath all of this, is something most people have not sat with long enough. The majority of the universe, the vast and overwhelming majority of everything that physically exists, is composed of things that your body cannot feel, your eyes cannot see, and no instrument built from ordinary atoms has ever directly measured. Dark matter. It has mass. It bends space-time. It holds galaxies together by its gravitational influence. But it does not emit radiation. It does not absorb radiation. It does not participate in the electromagnetic interactions that govern virtually every physical process you have ever personally experienced. The standard assumption for decades has been that dark matter communicates with visible matter only through gravity. But gravity is a very slow and imprecise messenger. What if there is a faster channel? What if a fifth force threads through both worlds simultaneously, connecting the observable sliver of the cosmos to the invisible majority? And what if the first fragile impression of that force was precisely what appeared in those measurements? Physicists speak in guarded language. They say things like suggestive deviation and warrants further investigation and is not inconsistent with new physics. The caution is professional and earned. But underneath the careful phrasing, there was something genuine, a period during which the universe appeared to be saying something new, and then went quiet again before anyone could be certain what the words were. Whether it was language or static, whether it was signal or coincidence shaped by desire, remains a genuinely open question. And that is the story. The deeper you go into the data, the less comfortable the ground becomes. Because the closer you examine the boundary between what we know and what we cannot yet know, the more you realize that the line between discovery and projection is not always easy to find. And the most unsettling possibility, the one this entire investigation keeps returning to, is that reality may be built in such a way that certain things are inaccessible, not in spite of how good our instruments are, but because of what we are made of. What if we almost had it? What if the signal was real, and we came close, and then the data shifted, and the certainty dissolved, and we were left with what we began with, a number that refused to be nothing but also refused to be proof. That question does not yet have a clean answer. Following it changes how you see everything. The muon is, in most practical senses, an inconvenience. Nothing in your daily life contains one. Nothing you have ever touched, eaten, seen, or breathed is made of muons. It does not compose atoms. It does not form molecules. It participates in no chemistry. It exists for approximately 2.2 microseconds, which is 2/millionths of a second, before breaking apart into other particles and vanishing as thoroughly as if it had never been. It weighs about 207 times more than an electron, its closest relative in the family of particles called leptons. And despite being, by any reasonable measure, entirely superfluous to the architecture of ordinary matter, the muon turns out to be one of the most sensitive instruments available to physicists attempting to detect physics that lies beyond the framework they have built, which is precisely why, when the muon began producing numbers that the theory had not anticipated, the field paid close attention. The experiment at Fermilab in Batavia, Illinois, carries the name muon G-2. The designation refers to a quantity called the G factor, which encodes how a particle's quantum spin responds to an external magnetic field, specifically how that spin precesses or rotates under the field's influence. Simple quantum mechanics, developed well before the modern theory of particles was complete, predicted that the G factor for both electrons and muons should be almost exactly 2. Then quantum field theory arrived and introduced the notion of virtual particles. Transient flickerings in the quantum vacuum, fluctuations that borrow existence from the fabric of space-time itself for intervals so brief they approach the edge of what is physically meaningful. Those virtual particles interact with the muon as it moves through space, and they nudge its G factor away from exactly 2 by a measurable amount. That shift is called the anomalous magnetic moment, denoted as a sub-mu. Calculating it with precision means accounting for every virtual particle the muon might interact with, every quark, every boson, every fleeting quantum echo that the universe permits. The standard model is capable of this calculation, extraordinarily capable in fact. The predicted and measured values were expected to agree to better than 1 part per million, an agreement so precise it should inspire a certain vertigo when you try to appreciate it honestly. But the Fermilab experiment was not checking whether the agreement was rough. It was looking for the difference between extraordinary agreement and perfect agreement. That difference, if it exists and is not explained by the theory, is where new physics lives. The physical apparatus of the muon G-2 experiment is worth describing with some care because it represents a kind of beauty that engineering occasionally achieves. The heart of the machine is a superconducting magnetic ring roughly 15 meters across, cooled to temperatures approaching absolute zero and generating a magnetic field so uniform that the researchers describe it as the most homogeneous such field ever produced in a laboratory setting. Muons are created by directing protons into a target material, selecting only those muons that are rotating in the preferred orientation and injecting them into the ring, where they circulate continuously while the magnetic field drives their spin to precess. Arrays of thousands of particle detectors distributed around the interior of the ring capture the signals from decaying muons. From the statistics of those decays, the physicists reconstruct the precession frequency with precision that requires no qualifier, because precision of that degree effectively defines its own superlative. Imagine a spinning gyroscope balanced on a surface that is gently tilted. The gyroscope's axis will begin to trace a slow circle, rotating around the direction of the tilt. The rate of that rotation depends on the gyroscope's physical characteristics, its mass, its spin rate, its geometry. Now substitute a muon for the gyroscope, Substitute the magnetic field for the tilt. The rotation of the muon's spin axis is the precession you are measuring. The difference between the rate you observe and the rate the theory predicts is the anomalous magnetic moment. If the muon precesses faster than theory expects, something is interacting with it that the theory failed to include. The experiment's origins trace back to Brookhaven National Laboratory in New York, where an earlier version of the apparatus ran during the late 1990s and early 2000s and produced a result that was tantalizing without being definitive, showing a small discrepancy that could have been a fluctuation in the statistics. The entire 50-foot magnetic ring was subsequently transported to Fermilab. The word transported understates what actually happened. The ring was too delicate, too precisely calibrated to take apart and rebuild without risk to its extraordinary uniformity. It was loaded onto a flatbed transport vehicle and moved in its entirety, 800 miles across the American Midwest, through closed highways, beneath power lines that had to be temporarily raised to allow passage, in a nighttime convoy that drew its own audience of onlookers and briefly became national news. That transport required 15 months of planning. Data collection at Fermilab began in 2017. In April of 2021, the collaboration announced its first results. The Fermilab measurement confirmed and strengthened the discrepancy from Brookhaven. The combined result showed the measured value of A sub mu sitting above the standard model's prediction by approximately 2.4 parts per million. Read that number and feel what it means. 2.5 parts per million in a theory that is accurate to better than 1 part per million. In that world, the discrepancy is large. The combined statistical significance reached 4.2 sigma, close enough to the 5 sigma discovery threshold to generate genuine excitement while remaining far enough away to require continued investigation. What made the deviation especially compelling was not only its magnitude, but its character. The muon precessing faster than theory expects means that something is contributing to its interaction with the magnetic field that the calculation did not account for. Virtual particles from known physics produce contributions that have been calculated to extraordinary precision. An additional contribution from an unknown particle, a new force carrier of a type the standard model does not include, would push the precession in exactly the direction the data was showing. The muon cannot identify what touched it. It does not retain a record of which interaction pushed it slightly off the predicted course. But the measurement can tell you that something did. Something the theory left out. Something that interacts with muons in a way that leaves this specific and quantifiable mark. What happened next, the theoretical shift that would complicate the entire picture, we will return to in time. But for now, hold the image. A muon, the universe's most inconvenient particle, circling through a magnetic ring in Illinois, wobbling a fraction too far, quietly, precisely, waiting to see whether anyone following the numbers closely enough would notice. Someone did. 4,000 kilometers east of the Illinois Prairie, in the rock beneath the Swiss-French border near Lake Geneva, another set of measurements was producing numbers that didn't fit. And the reason this story needs to connect directly to the muon rather than standing on its own is that 2 completely separate anomalies, emerging from 2 entirely different machines, studying 2 entirely different families of particles, both pointing in the same direction, is a different kind of result than either one alone. Coincidence is a story that requires justification when it repeats itself. The LHCb experiment at CERN was built with a narrow and specialized purpose. While the largest detectors at the collider function, like wide-angle cameras positioned symmetrically around the collision point to capture any new physics that might emerge from high-energy proton impacts, LHCb was designed to study the behavior of a specific class of particles called B mesons. These are particles containing what particle physicists refer to as a beauty quark, or sometimes a bottom quark. They live for roughly 1.5 trillionths of a second before decaying into lighter particles. The value of studying them comes from the sensitivity of their decay products to influences from physics that lies beyond the standard model. Tiny perturbations from new particles or new forces can shift decay rates in ways that, while small in absolute terms, are detectable by an instrument designed specifically to look for them. Rather than hunting for new particles by creating them directly, the strategy is to monitor the behavior of familiar particles and watch for fingerprints of something unfamiliar influencing the process. Among the most precise and theoretically clean predictions the standard model makes about B-meson decays is a property called lepton universality. Leptons are light particles, electrons, muons, and their associated neutrinos that do not respond to the strong nuclear force. The standard model asserts with mathematical rigor that the weak nuclear force, the interaction responsible for certain kinds of radioactive decay, should behave identically with respect to electrons and muons, once you correct for the difference in their masses. This is lepton universality. It is not a casual assumption or a convenient approximation. It is a direct consequence of deep symmetries embedded in the mathematical structure of the theory. If a B-meson decays and produces a lepton among its products, the probability of producing an electron versus a muon should, after mass corrections, be exactly the same. The universe has no reason to prefer one over the other. L, C, B watched B-mesons decay, and the decays were not balanced. The ratio of decays producing muons to decays producing electrons was consistently lower than the standard model predicted, not drastically, not in a way visible to casual inspection, but with a statistical pattern that grew more pronounced as the data accumulated and that eventually reached levels that warranted serious attention from the collaboration and from the broader theoretical community watching from outside. In certain measured channels, the deviation was approximately 15%. 15% sounds modest at first encounter. Inside a theory that predicts precise equality and has been confirmed independently in many other measurements, 15% is not modest. It means the universe appeared to be treating muons differently from electrons in a context where it emphatically should not be doing so. Something was tipping the balance. Something was suppressing muon production, or equivalently elevating electron production, in a way the standard model has no mechanism to explain. Consider what it means to observe a systematic preference in a large data set. A single unusual outcome proves nothing. 100 unusual outcomes in the same direction becomes harder to explain as chance. 1,000 outcomes maintaining the same ratio becomes increasingly difficult to dismiss. L, H, C, B was watching the equivalent of tens of thousands of coin flips that kept landing slightly more often on one side, persistently, consistently, regardless of how the analysis was divided or re-examined. At some point, the statistician stops saying unusual luck and starts saying the coin is not balanced. What could produce this? The standard model contains no answer. Lepton universality is not a preference or a default that can be overridden by sufficient energy. It is a symmetry. Violating it requires the introduction of something that does not appear anywhere in the theory, some new particle mediating an influence that treats electrons and muons differently. The model's theorists began constructing to explain this violation were precisely the same kinds of objects being invoked to explain the muon's anomalous magnetic moment at Fermilab. New heavy bosons, leptoquarks, exotic carriers of a potential fifth force that coupled preferentially to second-generation leptons over first-generation ones. The striking feature here, the one that transformed two interesting results into a genuinely alarming pattern, is independence. The muon G-2 experiment was measuring an entirely different physical quantity using a completely different technique at a facility on a different continent. It had no direct experimental connection to LHCb. The two experiments shared nothing except this: both anomalies specifically and centrally involved the muon. The muon was the linking thread. In physics, when independent measurements using independent methods both point at the same particle, the community begins to treat the coincidence as something requiring explanation rather than dismissal. A theory was beginning to crystallize. What if there is a force that does not behave the way the four forces we know behave? Not a force that acts on all massive objects the way gravity does, or on all charged particles the way electromagnetism does, but a force that selectively, almost surgically, engages with one specific type of particle. A force that knows about muons and largely ignores everything else that ordinary matter is built from. A force whose interactions with the muon could simultaneously produce an excess in its magnetic precession and a deficit in its presence among B-meson decay products. A force that, by the nature of what it couples to and what it ignores, passes invisibly through every proton, every electron, every atom you have ever touched. For a period of years, the universe appeared to be demonstrating a preference. Then, as we will get to, something changed. But the shape of the pattern needs to be clear before we can honestly trace its dissolution. There is a point in scientific investigation where the evidence, though insufficient to confirm, becomes sufficient to name. The anomalies had reached that point. Theorists across dozens of institutions began producing papers, hundreds of them in a short span of time, attempting to identify the category of physics that could simultaneously account for both the muon G-2 discrepancy and the lepton universality violation in B-meson decays. The most widely discussed candidate acquired a description: a fifth fundamental force. To understand what that phrase actually means, it is worth briefly explaining how forces function in the quantum mechanical description of reality. We experience forces as pushes and pulls, as attraction and repulsion, as the sensation of weight and the warmth of radiation. But in quantum field theory, forces are not actions at a distance or direct physical contacts. They are mediated by particles. Specific particles called bosons serve as messengers, carrying the force between the matter particles that interact through it. The electromagnetic force is carried by photons. The weak nuclear force is carried by W and Z bosons. The strong force that binds quarks together inside protons is carried by gluons. Every force has a carrier. If a fifth force exists, it must have one too. The most frequently discussed candidate for the carrier of a muon-specific fifth force carries the name Z prime boson. The label is deliberately chosen to evoke the Z boson that mediates the weak force, because the Z prime would play an analogous structural role, exchange between interacting particles as the mechanism through which the force acts. The crucial difference is in what it couples to. Where the known Z boson interacts with essentially all fermions, the Z prime in these proposals would interact strongly with muons and potentially with dark matter particles, and barely at all, or perhaps not at all, with electrons and the quarks that compose protons and neutrons. This selectivity is not physically forbidden. The strong force itself interacts with quarks while ignoring electrons. The novel aspect of the Z prime is not that it discriminates, but that the specific discrimination it performs corresponds precisely to the anomalies being measured, and that it has not appeared directly in any detector, implying it must be either heavy enough or weakly enough coupled to have escaped detection so far. A second category of candidate is the leptoquark, a hypothetical particle with a property that nothing in the standard model possesses. It carries simultaneously both lepton number and baryon number, meaning it can interact with both leptons and quarks in a single interaction vertex. This might sound like a technicality, but the physical consequence is specific and relevant. A leptoquark could directly mediate the B meson decay that LHCb was measuring, converting a bottom quark to a strange quark while simultaneously influencing the ratio of muons to electrons in the final state. Leptoquarks appear as predictions in several extensions of the Standard Model, including some approaches to grand unification, and searches for them at CERN have come up empty, meaning they would need to be heavy or weakly coupled to have remained undetected. Both of these candidates share a characteristic that could be called, with minimal exaggeration, elitism. They would not distribute their interactions broadly and democratically across all matter the way gravity does. They would discriminate. They would attend to specific particles and pass through others as though those others did not exist. And this discrimination, this preferential coupling to muons over electrons, is the feature that makes the fifth force hypothesis more than merely an additional entry in a catalogue of proposed particles. It points toward a force structured around a different logic of interaction, a different layer of the universe's physics, to which ordinary matter, as we know it, is nearly entirely deaf. Consider what that means concretely. The electromagnetic force governs your existence at the cellular level. It holds your electrons bound to their nuclei. It enables the chemical reactions in your metabolism. It carries the sensory signals through your nervous system. It mediates every interaction between your body and the external world that does not involve gravity. You participate in electromagnetism because you are made of electrically charged particles. You have the charge. You have the quantum numbers. You have the properties required to interact. The fifth force in this framework would require a different charge entirely, a different quantum property that ordinary matter does not carry or carries only in trace amounts, something that the muon possesses and the electron does not, at least not in the same way. The signal of this force would pass through you continuously, through every object in the room, through the building, through the planet, not difficult to detect, not weak in any conventional sense, but physically unable to interact with anything you are made of because nothing you are made of has the relevant property. A frequency that your receiver is not built to register. The broadcast moving through you in every moment, unheard, unfelt, leaving nothing. This is where the fifth force hypothesis stops being merely interesting and starts becoming unsettling. Because a force that couples to muons but not to ordinary matter raises an obvious question. What else does it couple to? If ordinary matter is excluded from its interactions, what is it primarily for? What does it interact with strongly, if not with the protons and electrons that build the visible world? And the answer that theorists kept arriving at, the one that gives the fifth force hypothesis its most profound implications, was the same answer every deep question in modern cosmology eventually reaches. Dark matter. Here is an analogy I want you to work with rather than simply read. Suppose the full range of ways that matter and energy interact with each other, every possible mechanism through which the physical world communicates with itself, were laid out like the electromagnetic spectrum. From the lowest frequency oscillations, measured in wavelengths longer than continents, to the highest energy gamma radiation, measured in wavelengths smaller than atomic nuclei, every channel, every possible carrier of information between physical systems. Now consider that we, as organisms assembled from atoms and governed by four specific forces, are tuned to an extraordinarily narrow portion of that complete range. Our biology responds directly to a few octaves of visible light. Our instruments extend our reach across the electromagnetic spectrum to radio frequencies, to X-rays, to the microwave residue of the Big Bang. We have built detectors sensitive to gravitational waves, actual oscillations in the geometry of space-time itself. Our experimental reach is immense compared to our biological baseline. but it is constrained at a fundamental level by the forces that our instruments are made of. An instrument built from ordinary atoms can only respond to forces that act on ordinary atoms. Now extend the thought. What if there are force channels, interaction mechanisms, ways that matter can exchange energy and momentum that operate through quantum properties that ordinary atoms do not carry? What if there are signals traveling through the room where you are sitting that are not weak, not faint, not in need of better amplifiers, but simply operating on a channel that your equipment is constitutionally incapable of receiving? Not because the signal is quiet, because the receiver is made of the wrong substance. This is not imagination. It is a serious scientific framework for thinking about the implications of the fifth force hypothesis. And what makes the muon important in this picture is its peculiar intermediate status. It is not ordinary matter in the way a proton or an electron is. It is short-lived, exotic, produced only in specific high-energy contexts. But it is also a particle with properties that differ from electrons in ways that are not yet fully understood at the theoretical level. If a fifth force exists that couples to muons but not to electrons, the muon is not simply an overweight electron. It is a partial bridge, a particle born into our world but possessing one property that tunes it, however, faintly, to a different channel. A particle that can briefly pick up a transmission that the rest of ordinary matter cannot hear. This explains the pattern in the anomalies. Not just that two results were surprising, but that both specifically involved the muon. If there is a force that the muon feels and the electron does not, then the muon's magnetic precession will be affected in ways the electron's is not, and B meson decays that produce muons will be treated differently from those that produce electrons. The muon is the common denominator, not by coincidence, but by physics. It is the only ordinary matter particle that sits, however partially, within the range of this hypothetical new interaction. The troubling corollary, which is worth sitting with rather than moving past, is what this implies about conformation. If the fifth force couples so weakly to ordinary matter that its entire signature in measurements accessible to us consists of indirect statistical effects on muon behavior, then every piece of evidence we can gather will be indirect. We cannot look at the force itself. We cannot build an instrument that responds to it directly. We can only watch the muon and infer, from how it behaves in conditions we can control, whether something we cannot see is influencing it. That inference chain is long. Long inference chains are places where errors can hide, where motivated reasoning can quietly insert itself between the data and the conclusion, where the desire to find something can shape the interpretation of evidence that is ambiguous enough to support more than one reading. Is what we observed a genuine transmission from a frequency our instruments cannot normally access? Or were we sitting in silence and interpreting the sound of our own instruments as a message from somewhere else? That question, as uncomfortable as it is what this investigation has been attempting to answer. And to understand the magnitude of what the answer might mean, we need to be clear about the scale of what remains hidden. There is a number in modern cosmology that most people have heard without genuinely absorbing. Ordinary matter, the protons, electrons, neutrons, photons, and everything assembled from them, every star, every planet, every organism, every instrument, every measurement ever made in any laboratory in history, constitutes approximately 5% of the total energy content of the observable universe. 5%. The remaining 95% is divided between dark matter, accounting for roughly 27%, and dark energy, the remaining 68%, an even more poorly characterized phenomenon associated with the universe's accelerating expansion. We are going to concentrate on dark matter because it is the component most directly connected to the fifth force story. Dark matter's existence is not speculative. We know it is there through multiple independent lines of evidence, the most intuitive of which is also the oldest: the way galaxies rotate. When you measure the orbital velocities of stars at the outer reaches of a spiral galaxy, the numbers are wrong. In a system where mass is concentrated near the center, which is where the visible stars and gas are concentrated, outer objects should orbit more slowly than inner ones. This is Newtonian gravity operating as it always has. The planets at the outer edge of our solar system orbit more slowly than those near the Sun. But the outer stars of galaxies do not slow down. Their orbital speeds remain roughly constant regardless of distance from the center. The only explanation consistent with the physics we know is an enormous invisible halo of matter extending far beyond the visible boundaries of the galaxy, adding gravitational pull without contributing any detectable light. The amount of this missing mass is not a minor correction. It outweighs the visible matter in a typical galaxy by a factor of 5 or 6 to 1. There is roughly 5 times as much dark matter as visible matter in the average galaxy, and our measurements of its distribution come only from the gravitational distortions it produces in the behavior of things we can see. What dark matter is made of, we do not know. What forces it responds to beyond gravity, we do not know. Whether it has any non-gravitational interactions with ordinary matter, we do not know. Vast underground experiments have been constructed to try to detect dark matter particles directly. Chambers of liquid xenon or germanium crystals or liquid argon shielded from every known source of background radiation, and none of them have produced a confirmed detection. Dark matter, whatever it is, interacts with ordinary matter at most very weakly, if it interacts non-gravitationally at all. Here is where the fifth force hypothesis acquires its deepest significance. A force that couples to the muon sector of visible matter and simultaneously couples to dark matter would be something with no precedent in our current understanding. Not just a new particle, a bridge, a non-gravitational channel of interaction between the 5% we can study and the 27% we can only infer from its gravitational effects. The Z-prime boson or leptoquark that the anomalies seem to demand could, in principle, mediate interactions that connect these two domains. Exchanged between a muon and a dark matter particle, the way a photon is exchanged between two charged particles. If this were true, the muon anomalies would represent something categorically different from previous discoveries in particle physics. Finding the Higgs boson confirmed an existing theoretical prediction. Finding a new quark added an entry to a catalogue. What the fifth force would represent, if the anomalies pointed at it correctly, is the discovery that ordinary matter and dark matter are not isolated from each other except through gravity. That there is a direct interaction, a force link, connecting the visible minority to the invisible majority. That the universe we have been studying is not the whole story, but a specific layer of something far more complex, and that another layer is accessible, however faintly, through the behavior of one specific particle we happen to have access to. That is not a small discovery. By any reasonable measure, that would be the most important result in the history of physics, which is precisely why the complications that followed in the data deserve to be examined honestly, without either catastrophizing the negative developments or clinging to the interpretation the evidence no longer cleanly supports. This section is clearly labelled speculation, because what follows is theoretical physics, which means it is a description of what is mathematically possible and physically motivated, not a description of what has been confirmed. But theoretical physics built on motivated foundations sometimes points at things that turn out to be real, which is why it deserves honest engagement rather than dismissal. If a fifth force connects the muon sector to dark matter, then dark matter is not merely a diffuse cloud of gravitationally active particles floating around in halos. It may have its own internal physics, its own forces, its own equivalents of the interactions that generate the complexity visible matter exhibits. Consider what happens to visible matter when you give it more than one force. Gravity alone produces gas clouds and planetary systems. Add electromagnetism, and you get atoms, molecules, chemistry, biology, everything. The richness of the visible world exists because there are multiple forces mediating different types of interaction between different classes of particles. If dark matter possesses its own analogue of the electromagnetic force, mediated by a particle theorists call a dark photon, it could form dark atoms, dark molecules, dark chemistry perhaps. In extreme concentrations under gravitational compression, it might produce dark stars, objects in which dark matter accumulates until its self-interaction produces the conditions for some analogue of nuclear processes. Entire dark astrophysical structures, invisible not because they are distant, but because they emit a form of radiation, our instruments have no mechanism to register. There is no observational evidence for any of this. The structures, if they exist, are genuinely inaccessible to every instrument made from ordinary matter, but the framework is not physically forbidden, and whether it applies to reality or not connects directly back to the fifth force anomalies. If the anomalies are real, if the fifth force exists and couples between the muon sector and dark matter, then the dark sector is not a featureless gravitational fog. It is a world, invisible to us, operating on channels we cannot receive, physically overlapping with our space while remaining structurally inaccessible to our instruments, passing through us every moment of our lives. If the anomalies are noise, the entire edifice collapses back to speculation with no experimental anchor, which is why what follows, the engineering, the machines, the scale of the effort to resolve the question, matters so much. There is a tunnel in a ring shape beneath the farmland and villages along the Swiss-French border whose circumference is 27 kilometers. If you drove a car along its length at highway speed, a single lap would take approximately 16 minutes. The tunnel descends between 50 and 175 meters underground, bored through ancient geological formations that were once the floor of a shallow inland sea. The project cost in the range of $10 billion. Construction involved engineers, physicists, and technical specialists from more than 100 countries. From above the surface, the installation is unremarkable. A scattering of nondescript buildings in the countryside near Geneva, connected by elevator shafts to something entirely different happening far below. The Large Hadron Collider operates at a temperature of 1.9 Kelvin, 1.9 degrees above absolute zero, the theoretical floor below which no further reduction in thermal energy is possible. By comparison, the average temperature of empty intergalactic space, warmed slightly by the residual radiation from the Big Bang, is approximately 2.7 Kelvin. The LHC is colder than the cosmic background, colder than Pluto's surface, colder than almost any environment that occurs naturally anywhere in the observable universe. Maintaining this requires approximately 10,000 tons of liquid nitrogen for initial cooling and more than 120 tons of superfluid liquid helium distributed through a continuous refrigeration system that runs the full circumference of the ring. The reason for the extreme cold is not atmospheric. The superconducting magnets that guide the particle beams can only achieve the zero resistance electrical state required for their function at temperatures this close to absolute zero. A localized warming by even a small fraction of a degree can produce a quench, a sudden loss of superconductivity that releases the stored magnetic energy in a pulse capable of damaging surrounding components. The LHC has experienced quenches. They are not routine events. Inside this refrigerated ring, protons are accelerated through a sequence of increasingly energetic preliminary stages before injection into the main collider, where two opposing beams circulate in opposite directions. At their operating energy, the protons travel at 99.99999% of the speed of light. At those velocities, relativistic effects become significant not just for textbook discussion, but for the engineering itself. The apparent mass of the protons, as measured in the laboratory frame, increases enormously. The magnetic fields required to keep the beams on their circular path, generated by approximately 9,600 superconducting magnets of various types distributed around the ring, must be roughly 100,000 times stronger than Earth's own magnetic field. When the two beams intersect at the designated collision points, the energy released in each proton-proton encounter is, by the standards of everyday experience, tiny. The kinetic energy of a flying insect. But that energy is concentrated into a spatial volume smaller than a proton's radius. The energy density achieved in that volume equals conditions that last existed freely in the universe approximately a trillionth of a second after the Big Bang. The particles that existed in that early moment, particles absent from the natural world for 13.8 billion years, briefly reappear in the collision debris, live for measurable fractions of a second, and decay into daughter particles that the surrounding detectors record. L, H equals C, B, the detector relevant to the B meson anomalies, differs from the large general-purpose detectors at CERN in its geometry and its purpose. Rather than enclosing the collision point from all sides like a spherical camera, LHCb extends along one side of the beam axis in a series of detector panels. This reflects the physics. B mesons produced in proton collisions travel preferentially forward along the beam direction, and LHCb is optimized to track them, follow their flight paths over distances of millimeters, and reconstruct their decays with a spatial resolution measured in tens of micrometers. For its Run-3 operation beginning in 2022, LHCb was substantially rebuilt. The trigger system, the electronic decision-making architecture that determines in real time which collision events to record and which to discard, was replaced entirely with a software-based approach. The upgraded system processes approximately 1 terabyte of data per second continuously. The computing infrastructure required to handle this occupies a room the size of a modest warehouse and applies machine learning algorithms trained on hundreds of millions of simulated events to classify incoming data in microseconds, evaluating whether each collision contains signatures consistent with heavy quark decays or potential new physics before deciding whether to retain it. Of the approximately 30 million collisions occurring at the LHCb interaction point every second, the vast majority are discarded in real time and permanently gone. Only a small fraction, events with the specific signatures the experiment was designed to study, survive to the storage medium. Run-3 also raised the collision energy from 13 to 13.6 tera-electron volts. That 6% increase, modest in percentage terms, meaningfully extends the accessible mass range for new particle production. If the Z-prime boson or leptoquark that the fifth force hypothesis requires sits slightly above the energy accessible in Run-2, Run-3 may be able to produce it. The higher luminosity, more collisions per second, also means that rare processes accumulate in the dataset faster, which is critical for the lepton universality measurements that depend on large statistical samples. With all of this, the highest energy proton collisions ever achieved on Earth, detectors rebuilt to unprecedented sensitivity, data processing capabilities that would have been unrecognizable to the physicists who designed the original LHCb, and the new particles that the fifth force hypothesis requires have still not directly appeared. No Z-prime has emerged as a clean peak in a mass spectrum. No leptoquark has been reconstructed from a particle track pattern that the standard model cannot explain. The indirect evidence, the statistical deviations in the precession of muons and the ratios of B meson decay products, those were present in the data. But direct evidence, the unambiguous signature of a new particle decaying into known particles in a way that nothing in the current theory permits, has not appeared. This places the investigation in an uncomfortable but honest position. Two interpretations are available, and neither is completely satisfying. Either the new physics is real, but either too heavy to produce at current collision energies, or too weakly coupled to appear in current data sets, in which case we are undershooting the target. Or the new particles are absent because they do not exist, the anomalies were fluctuations, and the standard model, tested more carefully than it has been in decades, remains correct. The largest machine ever built to probe the structure of reality has declined so far to deliver a definitive verdict. It has not confirmed the fifth force. It has not proven it absent. It has continued generating data that continues to be analysed, continuing to refuse the clean resolution that would allow anyone to write a final chapter. That refusal, that suspension of certainty across years of operation, may be the most accurate statement the universe has made to us in recent memory. Physics has a formal language for communicating confidence levels, and understanding it is essential for understanding how the fifth force story unfolded, because without it the headlines make no sense and the actual situation makes even less. When physicists present a result, they attach a sigma value, a number representing statistical significance. 1 sigma means there is roughly a 32% chance the result is a random fluctuation, nearly 1 in 3. That is not a number on which to base any conclusion at all. 2 sigma drops the fluctuation probability to about 5%, 1 in 20. Better, but still within the zone of results that vanish entirely as more data arrives, and the field has been burned by 2 sigma signals, often enough to treat them as directional hints at most. 3 sigma, which the community formally labels as evidence, with the deliberate caution built into the nomenclature, corresponds to a fluctuation, probability of roughly 0.3%. That sounds small. In particle physics, it is not enough. 3 sigma results have a documented history of dissolving under improved statistics. 5 sigma is the discovery threshold. The probability of a 5 sigma result being a statistical fluctuation is less than 1 in 3.5 million. The physics community, through extended painful experience, has concluded that below this threshold, the appropriate response is continued investigation rather than announcement. These standards are not bureaucratic conservatism. They are institutional scar tissue from a history of premature discoveries. The latter half of the 20th century in particle physics was punctuated by 3 sigma signals that generated conferences, papers, and excited theoretical commentary before evaporating when the data improved. The 5 sigma rule is the field's encoded memory of how powerfully the human desire to discover new things can distort the reading of ambiguous evidence. It is a structural protection against motivated reasoning built into the reporting conventions of the discipline. Understanding this calibrates the response to the anomalies correctly. The muon G-2 combined result sat at 4.2 sigma at its peak. The LHCb lepton universality deviations reached approximately 3.1 sigma in their most significant formulation, both firmly in the zone of serious scientific pursuit, neither at the discovery threshold. The community knew from experience that 4 sigma results sometimes grow into 5 sigma discoveries and sometimes regress into 1 sigma fluctuations. The only honest way to determine which story you are living is to acquire more data and watch the significance move. One of the most revealing practices in modern precision particle physics is called blinded analysis, and it deserves detailed attention because it exposes something important about the limits of human objectivity when humans are investigating phenomena they strongly hope to find. When an experiment is preparing to report a new result, the data is deliberately concealed from the analysis teams in a technical sense that prevents them from seeing the actual value of the quantity being measured until after every methodological decision has been made, committed to writing, and locked down. The analysts decide in advance and on record exactly which events will be included in the sample, how systematic effects will be estimated and corrected, what statistical methods will be applied, how edge cases will be handled, what the final result will look like structurally. All of this is chosen, documented, frozen. Only after the entire analysis pipeline is sealed does the blind lift and the number appear. Whatever it is what the analysis produces, because the analysis cannot be retroactively adjusted to push the number somewhere more convenient. This is not an accusation against the integrity of physicists. The people running these experiments are careful, dedicated, and professionally committed to finding the correct answer, regardless of whether it confirms their theoretical preferences. Blinding is not protection against dishonesty. It is protection against something subtler and more universal: motivated reasoning. The human brain is a pattern recognition engine operating with strong prior expectations. When you have spent several years on an experiment and have a clear idea of what the result should show if your hypothesis is correct, your brain will evaluate methodological decisions differently depending on whether they push the measured value toward or away from your expectation. You will not be aware of this happening. You will find genuinely compelling reasons to make the choices that favor the signal, and you will believe those reasons are purely methodological. You will be wrong in a way that is nearly impossible to detect from inside your own reasoning process. Blinding removes the feedback loop. If you cannot see the number cannot influence your choices. Every methodological decision has to be justified on its own grounds, because you have no way to know whether a given choice helps or hurts the result's significance. The moment the blind lifts is, by the accounts of physicists who have experienced it, unlike any other moment in scientific practice. Years of work, thousands of decisions, countless iterations of debugging, arguing, testing, all converging into a single instant when a number appears on a screen, not a preliminary answer, not an estimate. The universe's answer, filtered through your apparatus, irreversible. Physicists describe those rooms as unusually quiet. The anomalies we have been following survived this process. The Fermilab muon G-2 result was blinded. The analysis was completed under the blind was lifted, and the number that emerged was higher than the standard model prediction by an amount the collaboration took seriously. The LHCb lepton universality measurements went through the same process repeatedly with independent data samples. Each time the blind lifted, the ratio deviated from the standard model's prediction of exact equality. These results did not appear because someone looked at the data until they saw what they wanted. They appeared because a methodologically controlled, pre-committed analysis procedure produced them. That is meaningful. That is by any rigorous definition evidence, not proof, not a discovery, but genuine evidence. The critical distinction is between 4 sigma and 5 sigma. In language, the difference sounds small. In practice, it can represent years of additional data collection on the world's largest machines, and during that time, things can change. Systematic effects that seemed well understood can reveal hidden complexity. The theoretical calculation against which the measurement is being compared can shift, or the signal can continue building toward the threshold and cross it. You do not know which story you are inside until the data tells you. And so the only honest posture is to wait, collect, analyze, and resist the temptation to decide the answer before the evidence has delivered it. The investigation lived in that suspended state for years, and what eventually happened as the data accumulated and the theorists worked harder was not the resolution the early excitement had seemed to be pointing toward. There is a kind of reversal in science that does not fit the narrative templates most people carry. Not the reversal where the discovery is confirmed and the press conferences happen and the Nobel citations are written. A different kind, quieter, and in some ways more instructive, where the context in which the measurement was being interpreted changes rather than the measurement itself. Where the theoretical target moves. Where it turns out that the map had an error that nobody knew about, not because anyone was careless, but because making the map required techniques that carried their own uncertainties, and those uncertainties were larger than anyone had fully appreciated. That is the kind of reversal that came for the muon anomaly. And to understand it properly, you need to understand the internal structure of the standard model prediction it was being compared to. The predicted value of the muon's anomalous magnetic moment is not a single calculation. It is a sum of contributions from three distinct sectors of physics, each computed by different methods, each carrying different levels of theoretical precision. The first sector is quantum electrodynamics, the theory of how electrically charged particles interact through the electromagnetic force. QED calculations are some of the most precise computations in all of science. The agreement between QED predictions and experiment represents one of the defining triumphs of 20th century theoretical physics, and the QED contribution to the muon's magnetic moment is known so well that it contributes negligible theoretical uncertainty to the total. The second sector is the weak interaction, whose contribution is also calculable with high reliability and does not represent a source of meaningful uncertainty. The third sector is where the problem lives. The strong interaction, the force that binds quarks within protons and neutrons, also contributes to the muon's magnetic moment through a mechanism called hadronic vacuum polarization. Virtual particle-antiparticle pairs involving quarks and gluons fluctuate in and out of existence in the space around the muon and perturb its spin. This is the same basic mechanism as the QED contribution, but the mathematics governing it are fundamentally different in character. At the energy scales relevant to the muon's magnetic moment, quantum chromodynamics, the theory of the strong force becomes what physicists call non-perturbative. The standard technique of organizing a calculation as a series of increasingly smaller correction terms simply fails. The terms do not converge to a useful answer. For decades, this problem was handled through an indirect approach. Rather than calculating the hadronic contribution directly from the theory, physicists extracted it from experimental measurements of electron-positron annihilations, in which electrons and positrons collide, annihilate, and produce hadronic particles whose measured properties can be fed into calculations that yield the required hadronic contribution to the muon's magnetic moment. This data-driven extraction, refined over many years using results from multiple accelerator facilities worldwide, produced a number. That number became the standard model prediction against which Fermilab's measurement was being compared when the anomaly appeared. The difficulty, which began to surface around 2021 and intensified substantially through 2023 and 2024, is that this extraction method is itself a measurement, not a pure theoretical computation. It inherits uncertainties from the experimental data used to perform it and depends on analysis choices that carry their own systematic effects. A completely different approach to calculating the hadronic contribution began producing different results. Lattice quantum chromodynamics, which calculates the strong interaction properties of matter by discretizing spacetime into a computational grid and numerically solving QCD's equations on that grid using large-scale computing resources, offers an approach that is in principle more direct. It calculates the hadronic contribution from the underlying theory rather than inferring it from experimental data. As lattice QCD calculations matured technically and computationally, their precision reached a level where they could be taken seriously as a competitive alternative to the data-driven extraction. And when they were, they pointed to a higher value for the hadronic contribution than the experimental extraction had been providing. Higher meaning, if you take the lattice QCD result and plug it into the standard model's total prediction, the predicted value for the muon's anomalous magnetic moment moves upward, closer to what Fermilab actually measured. The discrepancy between theory and experiment shrinks. Let that sit for a moment. The muon is still precessing at the same rate the experiment measured. The Fermilab result did not change. What changed was the number being compared to it. The predicted value shifted, and if the lattice QCD approach is correct, the discrepancy that generated years of theoretical excitement about new bosons and leptoquarks and fifth forces was not, or not primarily, a window onto physics beyond the standard model. It was, at least partially, the result of using an imperfect technique to compute a theoretically challenging quantity and finding that the calculation was somewhat less accurate than the community had believed. At certain points in the evolving theoretical debate, the discrepancy appeared to shrink from 4 sigma to approximately 1 sigma. 1 sigma in particle physics is not a signal. It is fluctuation with a label. This is not a scandal. The experimental extraction technique was the best available approach for years and was validated internally by multiple independent groups. The lattice QCD approach was for a long time too computationally noisy to be taken as a serious competitor. The shift happened because both communities kept working, kept refining, kept testing their assumptions, and the field's collective picture of what the standard model actually predicts for this quantity became more uncertain, not less, as both approaches developed. The correct response to that increased uncertainty was exactly what occurred. Serious engagement with both approaches, ongoing debate about which is more reliable, continued effort to resolve the disagreement. As of the time this script was written, that theoretical debate is unresolved. The two approaches have not converged on a single agreed prediction. Both have identified potential systematic effects in the other's methodology. The theoretical uncertainty in the standard model's prediction for the muon's anomalous magnetic moment is larger than it was believed to be 5 years ago, and you cannot claim a 4 sigma deviation from a prediction that is itself uncertain. At LHCb, the lepton universality story followed a different path to a similarly sobering destination. As the redesigned detector accumulated data at its new rate and the improved analysis systems processed it, updated measurements of the B-meson decay ratios were released. The ratio that had appeared to deviate meaningfully from the standard model's prediction of exact equality between muon and electron channels in the earlier, smaller datasets began to move. A major update released in late 2022 showed the key lepton universality measurement sitting comfortably within the range the standard model predicts. The 15% deviation that had been the primary experimental basis for excitement about muon-specific new physics was gone. Not attenuated. Gone. No single moment of collapse. No meeting where someone announced that the fifth force was dead. Instead, a gradual shift in temperature. Papers proposing specific Z-prime models to explain the combined anomalies became less frequently cited. Conferences restructured their programs. The theoretical activity that had concentrated on these specific measurements dispersed toward other anomalies, other channels, other possible hints at other experiments. The field absorbed the non-result with the pragmatism of a community that has been through this before and knows how to redistribute its attention when a particular signal fails to materialize. What this story demonstrates is not a failure of science, but a demonstration of it. The Standard Model has now survived more than 50 years of increasingly precise experimental tests without producing a confirmed deviation. It did not survive by being defended. It survived by being tested, honestly and relentlessly, and found to be correct. The anomalies were not dismissed when they appeared. They were treated with the seriousness that unexpected data deserves. They were pursued with the most capable instruments and the most careful analysis methods available. They were followed until the data spoke clearly enough to shift the conclusion. The system worked. Whether that outcome feels satisfying depends entirely on what you were hoping to find. If you wanted the fifth force, this chapter is uncomfortable. If you wanted to watch science function as it is supposed to, without attachment to preferred outcomes, following evidence wherever it leads, this chapter is exactly that. The disappearance of an anomaly is not the same as a proof. That sentence may initially read as the kind of rhetorical cushioning that scientists use to preserve dignity after an expected result fails to appear. It is not. It is a precise epistemological claim that governs how science progresses at its outer boundaries, and taking it seriously changes the shape of this entire story. When a signal weakens as statistics improve, three genuinely distinct interpretations are available, and intellectual honesty requires holding all three simultaneously rather than collapsing into whichever one feels most congenial. The first interpretation is the most straightforward. The anomalies were statistical fluctuations. Small data sets behave unexpectedly with a frequency that mathematics predicts precisely. The lepton universality deviation in this reading was the physics equivalent of a biased-looking coin that turns out to be fair once you flip it enough times. The measurement approaches the correct value as statistics grow because the correct value is what the Standard Model predicts. This interpretation is supported by the trajectory of the LHCb data, which moved toward the Standard Model as the sample grew, and is consistent with the muon story, where the theoretical calculation turned out to be less certain than assumed. The 5 sigma threshold exists to prevent premature conclusions from small sample fluctuations. The anomalies never reached 5 sigma. The system worked as designed. The second interpretation is less comfortable to dismiss. The effect may be real, but smaller than the initial data suggested. The genuine deviation from the Standard Model may exist, but at a level that early statistics inflated into something more prominent than its true value. In this reading, the signal does not go to zero with more data. It settles at its true, smaller value, which remains non-zero. The updated measurements are consistent with the Standard Model within current uncertainties. They are not identical to the Standard Model's exact prediction with zero uncertainty. There is room within current error bars for a small but genuine deviation. And a small deviation, if real, is still a deviation. A 5% to violation of lepton universality is still a violation of a fundamental symmetry. It still requires new physics to explain. It is simply harder to confirm than a 15% effect, requiring more data, finer analysis, and more time. None of these requirements make the effect less real if it is there. The third interpretation is the one that shifts the shape of the narrative most substantially. The anomalies may have been pointing at something real, but not at the specific models constructed to explain them. The history of physics is not a history of correct first theories. It is a history of anomalies pointing imperfectly toward new frameworks that were not yet available. The perturbation in Uranus's orbit pointed at Neptune before anyone had identified Neptune. The failure of classical electrodynamics to explain certain properties of light pointed at photons before the photon had been conceived. The correct theory in retrospect is almost never the first theory proposed. It is the theory that explains not just the anomaly that motivated it, but a broader class of phenomena in a way that the initial proposals did not. The specific Z-prime bosons and leptoquarks that theorists proposed to simultaneously explain the muon, G-2 discrepancy and the lepton universality violation, with specific mass ranges, coupling constants, and interaction structures. Those may be wrong. The anomalies did not firm into signatures consistent with those specific models. But whether those models were wrong and whether something genuinely new exists at the relevant energy scales are separate questions. The models were early attempts to map a territory from an incomplete sketch. The territory may not have moved simply because the first maps were inaccurate. The broader context is also worth maintaining in view, because it is easy to lose when the focus narrows to specific anomalies. The standard model is known to be incomplete, not suspected, not hypothesized, known for several reasons that have nothing to do with the muon or B-meson anomalies. It does not include gravity. No quantum description of gravity consistent with the standard model's framework has been confirmed. It does not explain why the universe contains matter rather than an equal mixture of matter and antimatter. It does not account for dark matter or dark energy, which together constitute 95% of the universe's energy budget. It contains approximately 19 free parameters, numerical values like particle masses and coupling strengths that are not derived from any deeper principle but are inserted by hand based on experimental measurement. A complete theory would explain why those parameters have the values they do. The standard model treats them as inputs. The anomalies emerged from experiments designed specifically to probe where new physics would most visibly manifest if it exists at accessible energy scales. The strategy was correct. The methodology was sound. The anomalies were genuine in the sense that they survived rigorous analysis before weakening under improved data. Whether they were the leading edge of the physics that fills the standard model's known gaps, or whether they were noise that had the misfortune of appearing in particularly consequential-looking locations, remains genuinely uncertain. The honest acknowledgement of that uncertainty is not a failure of the investigation. It is the investigation proceeding correctly. The history of promising signals that eventually dissolved is worth naming without embarrassment. The Dharma experiment in Gran Sasso has reported a seasonal modulation in its detection rate for decades, a variation consistent with the expected change in dark matter flux as Earth's orbital motion alternates its direction relative to the dark matter wind. The signal is genuine in the sense that the modulation is present in the data. No other experiment using different detection technology has confirmed it. The ATLAS and CMS experiments at CERN both observed an excess of diphoton events at around 750 gigaelectron volts in 2015 to 2016 data. The excess generated extraordinary theoretical activity, hundreds of papers proposing new particles to explain it, conferences dedicated to its implications. More data arrived in 2016 and the excess was not present. It had been a fluctuation. These are not episodes of scientific failure. They are demonstrations that the statistical universe works precisely as the mathematics predicts it should. Fluctuations occur. They occur with diminishing frequency at higher significance thresholds, but they occur. The lesson is not that anomalies should be greeted with cynicism. The lesson is that enthusiasm should scale with sigma level, with independence of measurement, with the question of whether multiple unconnected experiments see the same effect. Calibrated excitement is not reduced excitement. It is excitement that survives exposure to more data. The muon G-2 theoretical tension is unresolved. The lattice QCD and experimental extraction approaches have not yet converged. LHCb data sets continue growing. Run 3 data is still being analysed. New experiments studying muon properties are in development. The investigations have not concluded. They have entered a slower, more demanding phase, the one that follows initial excitement when the readily available answers have been ruled out, and what remains requires more precision, more time, more sophisticated instrumentation, and more intellectual discipline about what is and is not yet established. For the fifth force hypothesis, not death, dormancy, the most promising indicators have quieted, but the theoretical possibility, a force selectively coupling to certain particle types, bridging visible and dark sectors, structurally undetectable by ordinary matter, remains mathematically coherent, physically motivated, and in principle testable given sufficient experimental capability. Whether that capability is achievable with instruments currently under construction is a question that will take years to answer. We have arrived at the place this story was always heading, not a conclusion, because there is no clean conclusion available, but a perspective that the preceding material makes accessible. A place from which the question that motivated all of this investigation can be seen more clearly. You are at this moment composed of approximately 10 to the 28th atoms. That is a number that language is not designed to accommodate. If you assigned 1 second to each atom, the counting would outlast the current age of the universe by an enormous margin. Each of those atoms is a nucleus surrounded by electrons in quantum probability distributions. Each nucleus is protons and neutrons. Each proton and neutron is quarks bound by the strong force. Every quark, every electron, every photon involved in the chemistry of your body responds to the 4 fundamental forces. The strong force holds your nuclei together. Electromagnetism runs every chemical and electrical process in your biology. The weak force governs nuclear processes that ultimately power the sun, whose energy sustains the biosphere you live in. Gravity holds you to the planet. 4 forces. Everything you have ever experienced, everything any human has ever measured, everything any instrument assembled from matter has ever detected, all of it operates through those 4 interactions, and those 4 forces, those particles, that entire framework accounts for approximately 5% of the universe's total energy content. Read that again with the attention it deserves. Not as a fact to be filed and moved past, but as a description of the situation you are actually in. The forces that built you, that sustain you, that connect you to every other thing you have ever touched or observed are the minority physics. They are the exception, the edge case, the small print at the bottom of a document whose main body you have never been able to read. 95% of what exists operates through mechanisms, follows rules, and produces structures that your atoms are constitutionally unable to register, not indirectly, not weakly, not in need of better instruments, constitutionally, built from the wrong material to participate in whatever is happening in the rest of reality. You are not just ignorant of the other 95% in the way you might be ignorant of events happening on another continent. You are structurally excluded from it. The physics of what you are made of does not include the interactions required to receive it. The muon anomaly and the LHCb measurements, all the years of careful work at Fermilab and CERN, were an attempt mounted from inside the 5% to reach, however indirectly, into the 95. Not directly. Not with any instrument made from ordinary matter in any conventional sense, but through the most delicate possible inference, watching the behavior of a muon in a magnetic field, counting the products of B-meson decays, looking in the behavior of accessible particles for fingerprints of interactions that ordinary matter itself cannot experience. And for a few years, the data looked as though something might be pressing from the other side, as though the boundary was thin enough in those specific experimental conditions that the mark of something beyond it could be seen in the statistics. The muon, that inconvenient and apparently purposeless particle that serves no evident function in the architecture of ordinary matter, appeared briefly as though it might be an antenna. A particle that belongs to our world but possesses one property that tunes it slightly to a frequency that ordinary electrons and quarks cannot receive. A bridge particle. The first evidence that the barrier between the 5% and the 95% is not perfectly sealed. Then the calculation shifted, the data improved, and the signal retreated. The universe, with the vast patience of something that has been operating for 13.8 billion years without any obligation to conform to human timelines, declined to confirm what the anomalies seemed to suggest. The theoretical landscape moved, the statistical picture clarified, the moment of almost knowing dissolved back into uncertainty, and the boundary reasserted itself. This is not the story that fits comfortably into a headline. Headlines announced possible fifth force evidence, unprecedented hints at new physics, cracks in the standard model's foundations. Those headlines were not inaccurate descriptions of the state of evidence when they were written. They were incomplete accounts of a story that was still in progress. The complete account includes what happened afterward. The Michelson-Morley experiment of 1887 attempted to measure the speed of light through the luminiferous ether, the invisible medium that 19th century physics assumed must pervade space as the substance through which light propagated. The experiment was remarkably precise. It found nothing. The speed of light was identical in every direction, regardless of the Earth's motion through space. The ether produced no measurable effect. This result confused the physics community deeply for years because it contradicted assumptions that were considered foundational. Nobody immediately knew what to do with it. 18 years later, Einstein built special relativity on the foundation that the ether does not exist, that the constancy of the speed of light is a fundamental feature of reality rather than a measurement anomaly. The null result, the precise and careful measurement of something that was not there, was the most important experimental result in physics of that era. Not a consolation prize. The discovery itself. We may be in an analogous moment. The specific models, the specific Z-prime bosons with specific coupling structures, the specific leptoquarks with specific mass ranges may be wrong. The anomalies did not consolidate into signatures consistent with those models. But what the investigation has established is not nothing. It has established that muons are exceptionally sensitive probes of physics beyond the standard model, more information per measurement than almost any other accessible particle. It has established that the theoretical calculation of the hadronic vacuum polarization contribution to the muon's magnetic moment was less well understood than the field believed, and that resolving the tension between the two competing calculational approaches is now among the most important open problems in theoretical physics. It has established that LHCb, with its new capabilities, will produce lepton universality measurements of unprecedented statistical power for years, and that any genuine violation at even the few percent level will eventually be impossible to conceal from it. And it has established, with more precision than was previously available, the location of the boundary of the standard model's confirmed validity. Knowing exactly where the boundary is, even when it turns out to be further away than hoped, is progress. Right now, in the room where you are sitting, you are likely being traversed by signals that nothing in your biology can register, not metaphorically, physically. Roughly 27% of the total mass in your galaxy is dark matter, distributed in a halo that fills the volume your planet occupies. Whatever dark matter is, whatever forces it does or does not respond to, it is passing through you. Through every person you have ever known, through every building ever constructed, through the rock beneath every continent, through the entire history of life on Earth, undetected by every measurement ever taken, because every measurement ever taken was made with instruments assembled from ordinary matter governed by four forces that dark matter does not appear to respond to. The fifth force may connect our world to that one. The anomalies may have been the first faint static from a channel that ordinarily produces only silence. Or they may have been noise that appeared in measurements sensitive enough to detect it and desperate enough to interpret it. We do not yet know. The instruments are still running. The data is still accumulating. The theoretical debate between competing approaches to the hadronic calculation is still unresolved. New experiments are in development. The story is in its slower phase now, the phase after initial excitement, the phase where what remains requires more precision and more time and more intellectual honesty about the distance between what the evidence shows and what the theory would prefer. Somewhere in the 95% that passes through you every moment, there may be a force that has been transmitting since before the Earth formed, through every atom that has ever composed a living thing, through every rock and every ocean and every atmosphere on every planet in every galaxy, leaving no trace in anything we have ever built to detect it. The anomalies pointed at it, briefly, or they pointed at nothing. The boundary between those two possibilities has not yet been precisely located, and the work of finding it, the patient, rigorous, methodologically honest work of narrowing the uncertainty until the question can be answered clearly, is the actual content of everything this story has described. The openness of the question is the real result, not a particle, not a confirmed force, not a signal from the dark sector with a name and a mass and a place in the next edition of the textbooks, but the precise and honest map of what is not yet known, combined with the knowledge of exactly where to look when the instruments capable of resolving it are eventually built. Understanding the exact dimensions of your ignorance is among the most useful things science can produce. It tells you where the next machine needs to point. It tells you which measurements to make when the statistics are better. It tells you where the universe has been keeping its secrets with the most care. The signal is still out there, or it is not. The question is still open, and the instruments are still listening,